Sanjeev starting first, but also there is a change in topic. So let me explain, and whom do you agree? I was some of what these tutorials were meant to be. I think has changed in the minds of some people, and certainly in the minds of me. I thought it was more of a tutorial is, strictly speaking, something of like seeing an overview of different certain field of the literature in a way that, but I think this is very difficult to do, certainly very difficult to do in a short period of time, and certainly this is not what has been the rule up to now. So then I've changed things a bit, or quite a bit. So what I have decided to do is to talk to you about two papers of mine, which illustrate the very diverse ways in which economists approach the use of networks, network theory, to the study of economic problems. The one of today is about bargaining, which is a fundamental phenomenon in economics that underlies many problems in economics. The one of today is bargaining in networks. The one tomorrow will be about globalization viewed from an economic perspective in networks. Today, methodologically, I use game theory, so it's basically a game theory application. Tomorrow, it's an application of the theory of complex networks, with very little, formally speaking, of decisions and game theory, although there is also a motivation underlying it, but it is peripheral to the project, okay? So I thought that these two papers of mine could illustrate different ways in which we economists think about problems of economic relevance from the point of view of networks, and that's what I therefore have decided to do. Okay? Very good. So this can also be used to. No. Ah, yeah? Okay. Very good. So, first, a very little motivation. Now, what is one of the central questions in economics? One of the central questions in economics is the relationship between decentralization and efficiency. Okay, we want to think of an economic system as a decentralized economic system. Okay, prices deliver that in economic systems, and we want to see the relationship between decentralization and efficiency, and how well behaved the system is. What is the paradigmatic approach that has been in the profession, perhaps one could say at least since Adam Smith, that of the competitive market. And we know what is the competitive market. The competitive market is the representation of a frictionless, anonymous mechanism of interaction through prices. And we know that under certain conditions, it delivers. It delivers in the sense that it produces efficient outcomes. This is the invisible hand of Adam Smith at work. Okay? It produces efficient outcomes, and it produces also, once we talk about prices, arbitrage-free situations, in the sense that because of the frictionless nature of the setup, prices are uniform. So, okay, there are no arbitrage opportunities. There is no transaction of the same good conducted at two prices, different prices. So this is therefore what we call an arbitrage-free situation. So then one important question, in line with what Sanjeev was also explaining this morning, is if we want to think of markets in a more realistic, less abstract sense, as something that takes place by people interacting, okay, and we model interaction through a network, to what extent that paradigmatic context can and the good features that it has can be achieved when there are some frictions, some realistic frictions. And then this can be strategic frictions, there can be matching frictions, there can be informational frictions, many frictions, okay? So in particular here we want to focus on two, strategic frictions and matching frictions. By strategic frictions I mean that people behave strategically. They don't take prices as given, but understand that they have an effect on prices and behave strategically. In fact, in this model, they will be determining prices by their behavior. And matching frictions, by that we refer to the fact that the people do not come together in a smooth, anonymous manner, but by a matching procedure, which can be less than, that can display frictions, and these frictions affect the outcome naturally. So this paper has, we want to summarize one key insight, has delivers the following main insight, that if the interaction mechanism that is mediated through bargaining is truly decentralized in a certain sense that I will specify, then the economy cannot really achieve efficient outcomes, okay? It has a fundamental, it cannot escape a fundamental generic inefficiency. And in what sense do we say that the mechanism is truly decentralized? Well, we want it to be decentralized in two senses. First, the pattern of interaction, which we will model as a network, is not given, but it is endogenously determined by the players themselves, who decide with whom to connect, okay? Anticipating what the consequences of that will be. Okay, so that will be one sense in which we want to think of the mechanism as decentralized. The pattern of interaction is endogenous. And then the matching process is also decentralized in the sense that we do not have people meet in a way that can be controlled from the center, so to speak, okay, in a centralized manner. But we just let people meet spontaneously, if you wish, okay, and therefore in a decentralized manner. So matching can be less than perfect because of that. Okay, so these are the criterion of decentralization that we want to consider, and we'll see that under those conditions, a realistic model of market interaction, realistic because it will not abstract neither from strategic nor matching frictions, will not be able to achieve efficiency. Okay? Okay.
In the context of networks, how would you define a frictionless setup?
Well, a frictionless setup would be one in which perhaps, well, in relation to these two criterion, where agents are taking their decisions in a non-strategic manner. So take prices as given, for example, or a context where matching doesn't display any frictions, but rather always achieves the best possible matching in a way that...
So if we're comparing we need to compare networks to networks, right? So we can't compare Adam Smith to networks because Adam Smith didn't define networks. So would you be comparing random graphs to whatever you're going to model, or are you going to compare?
No, I'm going to compare. That's right. Adam Smith didn't think about networks. He thought about...
He thought of it, but he didn't define them in a way formally that you will probably be defining them. So would it be Erdős-Renyi kind of graphs? What kind of graphs are you going to compare?
Well, so here, well, the graphs will be endogenous. So the graphs will be those that the agents themselves decide to form.
That's in your model, but what about the competitive frictionless setup to which you're going to be comparing it to? What graphs are those?
Well, in a frictionless setup, the framework is one where the interaction is not through networks, but through some generic black box we call a market, where
networks. They could be just throwing edges at the nodes randomly.
Well, but that's not how we typically, how the profession has typically modeled a frictionless market. Okay, it has basically it has typically modeled it as some entity through which the agents anonymously interact by reacting to prices, and the price is being determined endogenously to clear markets. So this is the paradigmatic description of what it means a frictionless market system. And we are looking into this box, okay, and insisting that the interaction between among people is personalized, is not anonymous, and has to respect a certain structure.
So you're not going to define a frictionless setup as a
No.
graph. You're just going to say that
Yes.
this abstract feature that has not been defined, so it doesn't really have any
But this is just by way of motivation, by the way. Okay, I'm not trying to do any. This is just by way of motivation, putting things in perspective of what I want to do. Okay, and for me, frictionless market system is just the Arrow-Debreu. I don't know if you are familiar with the Arrow-Debreu framework, where just the framework, the theoretical framework, where agents, what they said, react to prices, taking prices as given. Firms maximizing profits, consumers maximizing utility, subject to the value constraint. So then they don't interact with each other, they interact with the market via prices. And the prices are determined endogenously in a way that markets clear. Okay? This is a good idealized representation of some markets, in a sense approaching this idea of frictionless markets. But it is not like many other markets in the real world work. And we want to have a model that really incorporates notions that we think are important in the real world. That structure of interaction matters, that matching frictions matter, that the strategic considerations matter.
I can generate graphs.
Well, okay, you can do many things, but let me just proceed, okay? And I'll then at the end you come back we can come back to this. Okay, this is just by way of motivation. Okay. Okay, so the literature, this morning reviewing what I was going to speak about, of course, with 1 hour I couldn't talk about the literature, so I have a cross, skipped. Okay, we'll come back to this. Of course, I'm not the first one to talk about this at all. Okay, we built on a large literature, starting from Rubinstein, Bolinsky, and following with more recent work like that of Manea that also has incorporated bargaining into networks and try to address some of the issues that we are addressing here. Okay? Very good. Now, what I will be doing time permitting is I'll first talk about the basic model that I'm going to be talking about. It's a bargaining framework, pretty traditional in this literature, how it is modeled. In this framework, I want to discuss 4 notions that are key to our discussion. The notion of what is a decentralized matching mechanism, the notion of what is a situation where there are no arbitrage possibilities, that is, prices are arbitrage free. What notion of stability, of a strategic stability I will use to endogenizing the network. When will I say that the network is consistent with the incentives of players to connect or disconnect? And then I will talk about the notion of efficiency, that is our standard of a well-functioning system. We want to compare or to ask when the system is going to be efficient. So the analysis will start with a benchmark case, which will be the analysis of a complete trading network. By that I mean one where you have two sides, buyers and sellers, and all buyers are connected to all sellers and vice versa. So there are no restrictions that we want to impose ex ante. This is, in a sense, the case, the limit case, where from the point of view of interaction there are no frictions, because anyone can meet with anyone else. We want to study the game and the equilibrium in this context. Of course, this is the first step before going into arbitrary trading networks. Now the network will have a possibly very complicated structure. We want to understand when such networks will produce arbitrage-free situation, that is trading at a common price, when such networks might or might not be stable, what we will call pairwise stable, and then we will study the relationship between stability and efficiency. Okay? Yes?
So in the general case of these, then still bipartite networks, or can you have, say, intermediaries?
No, okay, so that's a good point. In contrast with what Sanjeev presented today, I am abstracting from intermediation, and I'm focusing on sequential intertemporal bargaining. Okay, so he abstracted from that and focused on intermediation. I'm doing, in a sense, the opposite. Okay, I'm abstracting from intermediation and really considering a much richer model of bargaining or of price determination. Okay, no longer posted prices, but an intertemporal process of bargaining. Okay. Okay, so the theoretical framework is very standard, the basic theoretical framework. So it goes as follows. There are some set of sellers, S, capital S, buyers, capital B. This is given. They're connected by some bipartite network, G. Okay? So links only exist between buyers and sellers. L is the set of links. And we assume that each supplier, S, little s, can produce at most one unit of the good. But the good is always homogeneous, so the good produced by a supplier is the same as the good produced by any other supplier. But what are not homogeneous are the suppliers. They have different costs of production. Let C sub S be the cost of production of seller S. For buyers, little b in capital B, we assume they care for just one unit of the good. The good, again, is homogeneous, so good for many suppliers is good enough for any particular buyer. But the buyers are heterogeneous in how much they value the good. Okay, so the value of little b is b sub b. So trading opportunities arise every period. So now think about time. Okay, introducing time. So trading opportunities arise every period, and in each of these periods, action is divided into two stages. Okay? Things are divided into two stages. First, matching is determined. So who gets to be matched with whom, and therefore bargain with whom. So this is the matching stage. Then there will be a bargaining stage. So how does bargaining actually proceed? So first about matching. So a matching, little m, is chosen. Of course, it has to be a matching that is consistent with the network G. So G is the network that specifies the trading and also matching possibilities. Okay? Okay, I'm seeing, okay, so matching simply just a specification of a set of pairs, pairs of buyers and sellers, okay, with the restriction that no buyer or no seller is involved in more than one pair. Okay, that's the.
And the matching is independent of the cost and of the valuation.
That's right. It's independent. Yeah. Hmm? So in fact, the way in which these matchings are selected is according to a certain probability distribution, phi, on the set of matchings that are consistent with capital G, that I call script M sub G. Okay. So there is some probability as to how a particular matching is selected. And some properties on phi will also be considered later. Yeah.
I have a question. And what is actually the network is doing here? So
The what thing?
Basically, feasible matching. This means that there should be an H between them. Yeah.
Yes. Exactly.
So basically, what you do if one node is connected to 4, you just merge them with either of these 4 with a certain probability. Yeah?
Yes, that's right. If there is an edge between, say, 1 and 4, 1 being a buyer and 4 a seller, for example, there is typically you want to assume that there is some probability
Yeah.
that in the matching chosen, 1 is connected to 4.
Okay, and they actually they produce and consume 1 unit per the whole time, or every period they need 1 unit.
This will be described in detail later, but they can produce and consume at most 1 unit, and once they consume, for example, the consumers and the producer produces that unit, they go away, and someone replaces. I'll be specific about this in a second. Okay. Now, let the matching be chosen as explained. And let me consider a link or a pair SB in the matching selected. What's happening for every such pair? What happens is the following, that one of the 2 agents, the buyer or the seller, is chosen at random to be the proposer. What does it mean to be the proposer? To propose a price at which the transaction is to take place. If the proposal P is accepted, then the trade occurs. If it's not accepted, it does not occur. If it occurs, what happens? Well, that the buyer earns the valuation minus the price. The seller earns the price minus the cost. And they go away. They are happy forever and ever. They are replaced by another buyer and another seller occupying the same position in the network with the same characteristics. This is a cloning type of economy, if you wish, okay? In which in every point in time, in every node, there is always a buyer and a seller with the same characteristics. Why do we do this? Well, we do this because this simplifies the analysis very much, because this means that at every point in time, the description of the economy is always the same, it's stationary. So will allow us very naturally to apply a stationary equilibrium concept. Okay? Yes?
So for the economy, it doesn't change if they accept the trade or refuse the trade?
No, for the economy, yes, that's right. No, so the economy looks the same forever after, independently of what, because yeah, they are, if they go, they are replaced by someone that looks exactly the same. Yeah, and if they don't go, they are the same. Okay, so this if the proposal is accepted. If the proposal is refused, then these agents remain still around next period. Okay, where everything again is done afresh in an stochastically independent manner. Okay. So this setup defines a game. Infinite stage game with infinite amount of people involved. At every point in time, only a finite subset is actually active. Okay, but you can think of it as an infinite amount of people involved there. Okay, not everyone playing at every point in time, only a subset of them. Okay, and we, being an infinite stage game in which things happen now and tomorrow and the day after tomorrow, we have to somehow make these intertemporal payoffs. We have to be able to compare and to aggregate these payoffs, and we do it as is usual in economics by incorporating a discount factor delta. Okay, that discounts future payoffs as compared to current payoffs. Okay. Let some notation. Let pi sub super ij, which is the same as pi super ji, denote the marginal probabilities that the link ij is induced by the probability distribution phi that selects the matching. Okay? The marginal on a particular link. Let V super ij be the surplus that can be earned in link ij. So that it is therefore the maximum of the valuation of the buyer minus the cost of the seller in that link, and 0. Then let's consider a subgame perfect equilibrium that is stationary, SSPE, that we denote by sigma. By the way, is every one of you familiar with the notion of subgame perfect equilibrium? No. Okay. So subgame perfect equilibrium is a Nash. Are you familiar with the notion of Nash equilibrium? Okay. So it's Nash equilibrium, but with the additional requirement that the strategies prescribe optimal behavior, not only for the contingencies for the situations that in fact happen in equilibrium, but all those that do not happen but could happen, but could have happened. Okay, so it's an equilibrium. So more concisely, is a subgame perfect equilibrium is a Nash equilibrium in every possible contingency. Okay, and roughly speaking. Okay, and then we are looking at stationary ones. So those are equilibria where the strategies do not depend on time. Okay, so we are looking at those type of equilibria. Okay, so being stationary, we can associate a particular payoff x sub I to node I. Okay, it's a function of the equilibrium, the network, and the discount factor. And what the vector of such equilibrium payoffs must satisfy? Well, it must satisfy a Bellman type equation, okay, in which basically there is a consistency between the equilibrium as considered today, the equilibrium payoff as considered today, and the equilibrium possibilities that can be considered tomorrow, with the corresponding probabilities, okay, that the continuation path goes in along each of these different possibilities. Okay, so this consistency, this Bellman type consistency. Are you? Does this? Okay. So basically, my payoff today must be a result of where I can go from today to tomorrow, the different possibilities, and the equilibrium payoffs that I will get tomorrow appropriately discounted. Okay. Okay, so this is a requirement of internal consistency. Okay, and this is what this condition expresses, which happens to determine uniquely the vector of payoffs. Okay, this in essence defines a contraction between equilibrium payoffs into equilibrium payoffs, a fixed point being an equilibrium. Because it's a contraction, there is a unique fixed point, therefore there is a unique vector of equilibrium payoffs. Okay? So you see, perhaps it is useful to go over this expression, just to clarify better what I was mentioning before. So let me see. So xi is the equilibrium payoff of node I. Okay. So you see, what's a way of writing this xi? Well, what things can happen from the perspective of player I? What can happen is that what can happen is First, that none of my links play is selected. This happens with probability 1 minus the sum over all my neighbors of pi super ij. Okay, with this probability, I'm not selected. Okay. So then my payoff, what would be in that case? It would be just the same payoff tomorrow, but discounted. So that's why you have the delta times the same xi that I have here. So that's one part of what should be in this xi. Right? Associated to the probability that none of my links is selected. Okay, so this is the payoff of I ex ante at the beginning of the period, before I know what's going to happen. Okay? But then, with the complementary probability to this, one of my links with some particular j is selected. Okay? So each ij is selected with this probability. Remember, this is the probability, the marginal probability that the link ij is selected. And then what can happen for any particular ij that is being selected? Well, it can happen that I am not chosen as the proposer. Okay? So then j is selected as the proposer. What will then j do? What will j do? He will offer to me, I, the minimum that I am willing to accept. And what is the minimum I want to accept? What I can get by going to the next period. This delta j. This delta xi. Okay? Why does it multiply by 1/2? Because this happens with probability 1/2 for every link ij. With the other probability 1/2, and this is what this term reflects, I am the proposer. What do? The opposite. Okay? I offer to this other guy, j, the minimum he is willing to accept, which is delta times xj. And I take the remaining part, provided it is positive, of course. Okay? So all these are all the possibilities that can happen ex ante before I enter into the period, and when appropriately weighted by all the probabilities of all these different possibilities, this must be equal to xi. Xi appears here and appears there, and so for every other xj, this defines the mapping that I was talking about. Okay? And it happens to characterize uniquely the equilibrium payoffs. Yeah?
I thought bargaining is where you don't know each other's valuations, so you.
Oh no, well.
You're assuming you know.
Yes, I should have. This is bargaining under complete information.
I see.
Yeah, there is bargaining under incomplete information, which is much harder. It's very hard.
When I think of bargaining in real life.
Yeah, of course.
You don't really know how much you.
Of course. So then you see, I mentioned strategic frictions and matching frictions. I could have mentioned as well informational frictions. These are not in the model. The model assumes them away.
I see.
Yeah. Okay, so then it turns out to be that this vector of equilibrium payoffs is unique, and in general is a function of delta, of course, of the discount factor, also of the network G, but of the discount factor delta. And I'm interested in seeing what these payoffs are equal to for delta very close to 1. What is delta going to 1 is a situation where agents are arbitrarily patient. They don't care so much about waiting. Is this realistic? No, of course, in the real world, impatience is an important factor. Why are we interested in this limit case? Because we are interested in this paper in understanding the effect of the network on bargaining and not other considerations like impatience. So therefore, we are just taking impatience away. We are abstracting from impatience by making delta go to 1. Okay? And therefore, the limit of the bargaining outcome, the limit of the bargaining payoffs when delta goes to 1 is what I call the limit bargaining outcome. Yes?
Could you still define this equilibrium mapping if the agents didn't have the trade-off between dying and selling or consuming? I mean, in this case, it's basically I have a trade-off between selling my product tomorrow or selling it today.
Yes.
If I can't do both.
You cannot do both, yeah.
How would this change if I could do both?
So probably you're referring to what would happen if I could store.
Well, or if I
I ca-
produced a good every time step. Does that change?
Every time step you produce, you produce a
one
good.
and you consume one every time step, rather than dying after producing it.
Rather than dying. No, so here you are so if an agreement doesn't take place,
You could
nothing happens.
Exactly.
No production takes place. If you wish, put it like this, okay? No consumption takes place, okay? And then you start from scratch next period. Now, what you are saying is, what if what I have produced, say I'm a supplier, I have produced, I haven't sold. What if I can then consider bringing it to the next period and selling it next period on top of the one I will produce next period?
Yes, and yeah, in a sense that's what I'm saying.
Yeah. Well, that is here. Here, if you wish, the goods are perishable. So if they are not, so if they are produced but not consumed, they're gone. Okay.
Well, if you didn't have to, if you didn't go, if the agent didn't die after selling his good, you would have a lower threshold for selling his good today, because he doesn't have face the trade-off of it.
No, but he doesn't. He only dies when he's happy.
Yeah.
In this model, he only dies when he's happy. So.
And don't let's not get hung up on it.
Yeah,
think about
that's
it.
it. Yeah. Okay. So, it's going to take a long time to describe what I want to say. So let's see. Okay, let me explain these 4 concepts, key concepts that are important for the analysis. Okay. One concept is the notion of the centralized matching process. When do I say that the matching process is decentralized? It's a property of phi, how the matches are selected. Okay. So a matching process, I say it to be decentralized when all the matching outcomes, matchings that are maximal in terms of set inclusion have positive probability. Okay? Of course, among the matches that are consistent with the network. Okay? I want to distinguish between maximal matchings and maximum matchings. Now, maximum matchings would be the matches that involve the highest number of pairs. Maximal matchings might not be maximum. Okay? Okay, so yeah, so let me just explain it in a different way. Suppose that matching takes place in this world in the following manner. People are in the street. walking around. Okay? Whenever two guys that are neighbors in the network find each other, meet, they go home and bargain that period. Okay? And so then they just walk around, okay, until what? Until there are no agents left in the street, which are neighbors that could meet and bargain. Okay. When this happens, then I could go on forever. Nothing is going to happen. Okay, beyond that. Okay. So then the outcome that results when this happens is maximal. But it could be very inefficient in a sense. In the sense of just very few people actually being matched and many people being left unmatched, okay? Just by how the pattern of matching has occurred. So because I want to insist that the matching process is decentralized, I want to insist that all matches that are maximal have positive probability. Because insisting on something different from that would presume that matching is implemented in a centralized manner. Okay? In a centralized manner. So allowing some people, forbidding some people that could match, not matching, in order to match them with some other people later, so that in the end, for example, the number of matchings is maximized. So I want to rule this out. So I want to insist that every maximal matching has positive probability. So this is my notion of decentralized matching. Okay?
Excuse me, but you insisted previously on having a complete information, yeah? So they all know each other's valuation.
Yes.
And they all know each other's costs.
Yes.
But then in a way this is quite deterministic because the guys would be just picking the guys with highest valuation and lowest cost.
No, if they yes, that would be if the matching was endogenous, something like this might very well happen. But the matching is not exogenous, endogenous in this model, but it's exogenous. Indeed, you could very well consider endogenous matching, in which the matching decisions of players would be motivated by payoff considerations, but this is not here. Okay? Yes. Now, then the notion of price arbitrage. When will I say that a network G is arbitrage free? I would say that the network G is arbitrage free if when the discount factor goes to 1, so basically impatience is not an issue, time is irrelevant in a sense, all trade is conducted at the same price. So the good is homogeneous, so therefore no arbitrage would require that price is uniform, is the same in all trades. Okay? That's when this happens, we say that when this happens for the equilibrium associated to a particular network G, we say that the network is arbitrage free. Okay? When will I say that a network, now I'm talking about endogeneity, how the network is formed. When am I saying that a network is strategically stable? When am I saying that the network is consistent with the incentives of the agents to form and destroy links? Well, I will say that the network is pairwise stable, that's what the term I use, when is such that none of the links in place in that network want to be deleted by one of the agents, and none of the links that are not in the network want to be formed by the two agents involved. Okay? So then the network will be said to be pairwise stable. Okay? Now there is an important twist here. That is that you see all these inequalities that reflect this thing that I'm saying are strict. So what this means is that in order for the link to be created or for the link to be maintained, I want there to be a strictly positive gain. So in case of indifference, I am presuming that there is some infinitesimal cost of maintaining or forming a link, so that the link will not be formed or maintained. Okay. And finally, networks are said to be efficient if basically maximize the total surplus that there is, okay, to be obtained. Okay, so let me start with a benchmark case. As I mentioned at the beginning, this is the case where every buyer is connected to every seller and vice versa. Now, if delta goes to 1, people have basically do not mind waiting. It's clear that all trade has to be conducted at the same price. Because if there were trade conducted at 2 different prices, the buyer that is supposed to be buying at a higher price would rather wait to be connected to a seller that is selling at a lower price and make the trade. Okay, so then it's clear that in a complete bipartite network there will be a unique trading price, or in other words, the complete network is arbitrage free. Now, there's a single price. How do we? How is this price found? How does it compare to the valorization competitive price? Well, the price can be uniquely characterized. Okay, so there's a unique price that at which trade takes place in a complete network. And it is basically the unique price that satisfies what property? The following property. The property that if trade was to be conducted all over the network at that price, the total surplus earned by the sellers, ex ante, in expected terms, of course, has to be equal to the total surplus earned by the buyers. So, this condition, if you sort of write it formally, characterizes uniquely the equilibrium price that has to, the unique equilibrium price, the uniform equilibrium price at which trade takes place in a complete network. Why intuitively this is the case? Well, the reason why this is the case is rather transparent. It's because, you see, think of a buyer and a seller, only a buyer and a seller, okay? Bargaining bilaterally. Now, they are in essentially symmetric situation, okay? Except that perhaps by chance, the buyer has been selected to be the first proposer, or perhaps the seller. But if the discount factor is very close to 1, this doesn't really matter very much who in the first place has been selected as proposer or as respondent. Is that right? So therefore, since they are, except for that, in fully symmetric situation, they should divide the surplus 50-50. Is that right? Now take the buyers and sellers, now there are many buyers and many sellers, all as a whole. By construction, in every link, one buyer, the buyer, or the seller is chosen to be the proposer. So then if we look at every link from the aggregate perspective of the buyers and the sellers, it's clear that as a whole, the buyers and as a whole, the sellers should get the same share of the surplus. Okay? Now thinking of the buyers and the sellers as a whole.
In the long run.
In the long run, yes, when delta goes to 1, which is, what do you mean in the long run? Well, in the long run, yes, in the long run, yes. So if you repeat this over time, yes, very good, yes, indeed, yes.
for a given valuation, why, if in the long run I'm very patient, why don't I wait? Why doesn't the cost of production converge? Because I'm happy to wait for somebody. If I know there's perfect information, I know that someone has a lower cost of production than somebody else, then I could argue, well, I have time to wait, so I can push the price down and wait for the lower production cost seller.
Of course, you can very well do that. Yes. But that is not what I'm saying. So what I'm saying is that if you look at the surplus, okay, that you are making, okay, by comparing your so you are the supplier, the price might. So let me look. Well, let me perhaps formulate it in a different way. So in the end, really, you are a buyer and I am a seller, okay? I don't know what is your cost, I don't know what is my valuation, but in the end, really, what we have is a pie to divide, a surplus to divide, okay? Which is simply just the difference between my valuation and your cost, or vice versa, I don't remember who was it, okay? That's in the end, okay, what really we are talking about. I happen to be connected to you, that you are a very efficient supplier. Fine, that's good for you and that's good for me as well. In the end, what we have is a surplus to divide. Okay? And if strategically we are in symmetric situations, that surplus will divide equally. And the way to divide that surplus equally is basically setting a price that is in between your cost and your valuation, and my valuation.
I agree, but if we are in the complete bipartite network and then we're also connected to Charlie and Charlie can produce it at a lower cost, why would you take my higher production?
Because this is okay. So this is clear bilateral. You know? Mm-hmm. Now, indeed, the price that we two agree on has to take into account that consideration, of course. Yes. I'm not saying I'm not objecting to that. What I'm saying is that when we want to determine this price that takes into account all those considerations, if we think as the total set of buyers and total set of sellers as a unit, the sellers and buyers are going to have the same opportunity to be the proposer, I'm not really clear very well. I'm not explaining it very well. I realize that.
So does it go along the lines of saying, because you can't distinguish between buyers and sellers, they're all, let's say, within the set of buyers and within the set of sellers, they all have the same degree, same connections, because it's a complete network. You then sort of coarse grain and look at sort of one representative seller and one representative buyer, then make the argument that you made before.
Well, but the thing is that here the valuations are, there is no such thing as a representative buyer and a representative seller, because buyers and sellers have different valuations and costs.
Well, there's sort of the average over the population that exists, right?
No, but here rather than the average, I'm taking just well, yes, in a sense,
the sum is like an average.
It's like an average, yes. If you want, you can think of it as as the average. Yes, in fact, because since the numbers are fixed, the average is just like the total is the average times the number. Huh? Yeah. Okay, so well, I'll elaborate on this later when with more time. Now, this unique price that is determined there could be compared to the valuation price, the market clearing price, and which is basically the price where the number of sellers willing to sell at that price, this is in some notation that I will not explain this set, is equal to the number of buyers that are willing to buy at this price. And in general, we find that it may not be the same. Okay? So this is already a possible source of inefficiency. Okay, so I don't have time to go over much more, but let me at least tell you what we do from here. Okay? What we do from here is the following. Okay, so we know what the benchmark, the complete network setup delivers. It delivers a uniform price, and it delivers a uniform price generally different from the market, the valuation price, or the competitive price. Now, we want to first ask for any G, possibly very incomplete, when will we have this? Okay? When? Clearly, the network G has to be connected. It cannot be separated into two different components, because then, of course, they would be isolated worlds. Okay, they have to be connected. But how? What topologically? What is required for this uniform price to arise in equilibrium? Okay, so then we characterize it. Okay. The average free networks. Right? And what does this characterization entail? It turns out to be something very reminiscent of what probably many of you know, the marriage theorem. Okay? When does a perfect matching exist? Okay? In a sense, it's a price version of the marriage theorem. Okay? So then, a network is arbitrage free if and only if there is price-based how would I call it? Price-based marriage theorem type condition satisfying. Okay, basically that every subset of buyers and every subset of sellers is globally connected to a set on the other side that in which this set of buyers or sellers is not constrained, okay, in a sense. Okay? But now constraint is constrained in terms of the bargaining price that they can assure themselves. Then we ask, well, about endogenous networks, which in our case are pairwise stable, okay? And then, well, we ask what sort of objects these are. Well, then we show that they are always arbitrage free. Well, first, they exist, okay? Right? Which, of course, in principle is not obvious, okay? But such a thing has to exist. We show it exists. We show that they guarantee the low one price, as we often call. Okay, that basically all trade conducted at the same price. And then we ask, are they efficient? Do they maximize the surplus? And the answer is no. And then the further question is why? Okay? Why is it that they don't? Okay? And does it have to do with the heterogeneity of buyers and sellers, buyers' valuation, sellers' cost? Or does it have to do with the topology of the endogenous network, those networks that are pairwise stable? And the answer is because of that, okay? Because of the endogenous trading constraints induced by a pairwise stable G. Okay. And what are these endogenous trading constraints captured by a pairwise stable G? Well, they happen to be such that they rule out too much connectivity and too little connectivity. Efficiency could be obtained if the connectivity was was very dense, very high, or it was very little. Okay. How? Well, let me give you an example. If the network is complete, there's total connectivity, okay, between the two sides of the market, then we already saw that the price is uniform. So abstracting from buyer and seller heterogeneity, we would have valuation price and efficiency. Now, suppose that instead you have the network being a collection of dyads, okay? So basically just buyer and seller connected independently. So one buyer to one seller, one buyer to one seller. So it was just a sequence of bilateral bargaining going on, unrelated. And then buyers and sellers would always connect in a way that they can really trade, because otherwise that would not be could not be a pairwise stable network. Then, well, again, as delta goes to 1, you would have trade at a price different from different dyads, depending on the cost and valuation, but trade in every dyad, and the surplus would be split. That would be efficient. Pairwise stability brings you somewhere in between. The network cannot, the complete network is not pairwise stable. Why? Because there are many links that are redundant and that will not be kept. This collection of dyads will typically not be pairwise stable. Why? Because if the price at which different dyads conduct their trade is different, there will always be incentive to form a link across by the buyer in the dyad at which the price is higher to the seller at which the price is lower. So when you put all these considerations together, okay, and embodied in particular in the notion of pairwise stability, the topological restrictions that this induces into the network prevent efficiency to be obtained. And why does it happen? Because the topology is such that you cannot rule out that there are maximal matchings that are not maximum. Okay, coming back to what we said at the beginning. Okay, the topology, okay, of a pairwise stable network is such that there will be for sure always maximal matchings that are not maximum. This will generate inefficiency always because there is less trade than what would be efficient that takes place. And in the end, produces the inefficiency conclusion that I mentioned at the beginning. That a pairwise stable, that an endogenous network, trading network, leads basically always to inefficient outcomes. I've gone 10 minutes beyond, okay, sorry, stop here. Okay.